Alright, so now let me show you one of the most important architectures used inside of the big tech product companies. So here we are talking about the system that tracks every user click, every scroll, every interaction, and turns it into real-time dashboards, recommendations, and business decisions. So we are talking about real-time clickstream pipeline. And here's why this matters. This exact architecture that we are going to see, or some variation of it, is used at companies like Uber, Netflix, LinkedIn, Amazon to power their product analytics systems at massive scale. But it's not just important in production. This is also one of the most frequently asked system design questions in senior and staff level interviews. And questions like designing a real-time analytics pipeline, building a clickstream processing system, or creating live dashboards all map back to this architecture. So in this video, we are not just learning theory, we are breaking down a battle-tested production-grade system layer by layer exactly the way you need to explain it in an interview, right? So let's start from the very beginning. Everything starts at the client layer, where user interactions are actually generated. Every time a user clicks a button, scrolls a page, opens an app, or performs any action, an event is created, right? This is the raw signal that drives the entire pipeline. Now to capture these interactions, we embed lightweight SDKs directly into the applications, right? Now on the web, this is usually a small JavaScript snippet that automatically tracks events like clicks and page views and sends them asynchronously so that it never blocks the user experience. Now on the other hand, on the mobile devices, things work a little differently because network conditions can be unreliable and battery consumptions do matter in the mobile devices, right? And so in case of mobile devices, events are typically batched first of all locally, and then they are flushed periodically or maybe during lifecycle events like app backgrounding, right? Now on the backend, server-side SDKs capture events such as payments or API calls, and these are usually more reliable and are often sent with lower latency, right? Now the key goal of this particular layer is simple, right? But it is critical as well. We want to capture every meaningful user interaction as reliably as possible without impacting the performance. And if we collect too aggressively, we risk slowing down the entire application. Also, if we collect too conservatively, we risk losing valuable data. So this layer is all about finding that balance, right? Now, once the events are generated, they don't go directly into the core system. Instead, they first pass through the edge collectors, which form the first ingestion layer. So edge collectors are deployed close to the users, both geographically and logically, often behind load balancers or CDNs, right? And the reason for this is to reduce latency and to absorb sudden spikes in traffic before they hit the core infrastructure. So at this layer, several important things happen. Each incoming event is validated to ensure it matches the expected schema, right? So that the malformed data is filtered out early. Then the events are enriched by adding useful metadata such as geolocation, derived from IP addresses, or device information extracted from user agents. And this enrichment step is important because it avoids expensive processing later in the pipeline, right? Now another critical responsibility of edge collectors is buffering. So instead of sending every event individually, events are first of all grouped into small batches and forwarded downstream. And it also provides a natural form of back pressure control if downstream systems slow down, right? So you can think of edge collectors as shock absorbers for the entire pipeline. Without them, sudden spikes in traffic could overwhelm the downstream systems and cause cascading failures. With them, the system remains stable even under heavy load, right? Now, after the events are validated, enriched, and buffered, they are sent into the backbone of the system, which is the message bus. And typically, we use Kafka to implement it. So Kafka acts as a distributed append-only log where all the events are stored durably on a disk. This means that every event is persisted and can be replayed at any time, which is extremely valuable for debugging, reprocessing, or backfilling of the data, right? And one of Kafka's biggest strengths is its ability to handle extremely high throughput, often processing millions of events per second by distributing data across partitions and brokers, right? Also, it enables a powerful fan-out model where multiple independent consumers can read the same stream of data without interfering with each other, right? And this allows different systems such as stream processors, analytics engines, and machine learning pipelines to operate in parallel. Now, another important feature of Message Bus or Kafka per se is retention. So Kafka allows you to configure how long the data is stored, ranging from a few hours to several weeks, right? And this gives you the flexibility depending on your use case. Now, the most important concept Kafka introduces is decoupling. Producers like SDKs and edge collectors are completely independent from the consumers like the processing systems. So this separation allows each part of the system to scale independently and prevents failures from propagating across the pipeline. Now, internally, Kafka organizes data into topics, which are further divided into partitions. And each partition maintains strict ordering, and consumers can track their progress using offsets within each partition, right? Now, this design enables both scalability and fault tolerance, although it comes with the trade-offs such as managing partition counts and balancing load, right? Now, once the data is safely stored in Kafka, it is ready to be processed in real time. So this brings us to the stream processing layer, often powered by systems like Flink or Spark structured streaming, right? And this is where raw events are transformed into meaningful insights. So now, unlike simple stateless processing, stream processors maintain a state. This means they can keep track of information across the events, such as user sessions or rolling aggregates. For example, events belonging to the same user can be grouped together to form sessions based on the time gaps between the interactions, right? And this concept of sessionization allows us to understand user behavior more meaningfully rather than treating each event in isolation, right? Also, in addition to sessionization, the system continuously computes aggregates such as counts, conversion rates, and funnels in real time, right? So now another important capability is routing. After processing, the data stream is split into multiple downstream paths. Typically, one leads to a real-time analytics store and another to a long-term storage system, right? And what makes this layer especially powerful is that it shifts the computation early in the pipeline. So instead of running heavy queries on raw data layer, we compute insights as the data flows through the system. And under the hood, systems like Flink use mechanisms such as checkpointing to ensure fault tolerance and exactly one processing guarantees. And also another important thing to note over here is that they operate on event time rather than the processing time, which allows them to handle out-of-order events correctly, right? So while stateful stream processing introduces complexity, it provides massive performance and scalability benefits, making it a cornerstone for modern real-time systems. Now, after processing, the data is sent to a hot OLAP store, which is optimized for fast queries. And this layer is designed to serve dashboards and APIs with sub-second latency, right? And this much latency even when dealing with billions of rows. So unlike traditional databases, OLAP systems uses columnar storage, which allows them to read only the required columns for a query, significantly improving the performance, right? Also, they leverage techniques like pre-aggregation and indexing to speed up the common queries, and many use vectorized execution as well to process data efficiently at the CPU level, right? Now, these are some of the examples which are commonly used over here because they are built specifically for high concurrency and low latency analytics. And this is the layer that powers real-time dashboards, which enables teams to monitor metrics as they change in real time, right? But while OLAP systems are extremely fast, they are not really designed for deep historical analysis or complex data transformations. That's why in parallel, we also send the data to a Lakehouse. So alongside the OLAP store, we send the same data to a Lakehouse. And this system is designed for flexibility and long-term storage. So it combines the scalability of data lakes with the reliability and structure of the data warehouses, right? And using formats like Iceberg and Delta Lake, it provides ACID transactions on top of object storage systems like S3 or GCS or ADLS, right? Also, this allows us to store months or even years of data, including both raw and processed events. And also it enables batch processing and machine learning workflows using tools like Spark and Trino. Now, one of the most powerful features of a lakehouse is time travel, which allows you to query historical versions of the data and track changes over the time, right? So the key idea over here is that we are serving two different needs using the same data. The OLAP store provides speed for real-time queries, while the lakehouse provides depth for complex analysis and long-term storage. Now finally we reach the consumption layer where data is turned into decisions, right? So this includes dashboards, APIs and alerting systems. Now BI tools like Superset, Grafana and Looker allow teams to visualize metrics and monitor performance, right? And query APIs expose the data to applications for use cases like personalization and recommendations, often with strict latency requirements, right? And finally, alerting systems continuously monitor metrics and trigger notifications whenever anomalies or thresholds are detected, right? And this enables the teams to react quickly to issues. So at this point, the journey from a simple user click to actionable insights is complete, right? Now if we step back and look at the full pipeline, we can see three major stages. The ingestion and the edge layer captures and stabilizes the incoming data. The stream processing layer transforms and enriches it. And the serving and storage layer delivers insights to the users and the systems. So each layer has a clear responsibility, which is what makes the system scalable, resilient, and easy to evolve. Now at the core of this particular architecture that we discussed, there are a few key design principles that we should know. First of all, we decouple the components to allow independent scaling and fault isolation, right? And we serve both real-time and historical use cases using different storage systems. Also, we push the complex logic into the stream processing layer instead of the query layer, and we design the replay by retaining the data in Kafka so that we can reprocess it whenever needed. So a real-time pipeline is not just about speed, it is about building a system that is correct, scalable, and resilient under massive load. And this is exactly the kind of architecture that powers modern data platforms at big tech companies. So if you truly understand this system deeply, you are already thinking at level expected in senior and staff engineering interviews, right? So I hope you understood this entire architecture well. And now in the next videos, I will be breaking down each and every layer of this particular architecture in great detail, and I will be going into the bottom of every component. So do stay tuned.